All right, we got section 7.3, the section that speaks volumes, because we're finding volume. It's play on words, it's not very funny. We start out actually with a little demonstration. So if we have a circle that is the base of our object, we're going to drop the base, all right? So there's like a can, like a cup. So the bottom of the cup, right? Except this shape, we're going to raise squares up. Oh, this is the rectangle. This is the triangles. I want this one. Drop the XY axis. There's the base. We're going to raise up squares, is what I meant to say, squares. And then we're going to sweep. This is the object that we're trying to find the volume of right here. And so we're sweeping, we're taking an infinite amount of squares, and we're going to add up all the areas, and when you add up all the areas, you get volume. This is actually the shape that we're looking at. So it's kind of like a building, is what it reminds me of, this weird kind of domed building. But anywhere there's a vertice on the square, that causes an edge to the building. This is the actual shape right here. And then this is sweeping the squares through. We want to find that volume. And we can, using calculus. The region R bounded by the relation x squared plus y squared equals 4 is the base of a solid. So we laid that circle down. That's the base. For this solid, each cross section perpendicular to the x-axis is a square. Find the volume of this solid. Well, here's the idea. Before, if we had y equals x squared, and we wanted to find the area under the curve, we use these rectangles. So here's the rectangles. And the rectangles, the height of the rectangles was this curve. So if we integrated the height times the base was the change in x as we go along, all those little changes in x. And we made them the same, and we had the Riemann sums. And so that's the height, and then the other dimension is the dx. So that when we integrated, this gave us the area. 2 dimensions, in other words, 2 dimensions. So this is 1 dimension, you integrate 1 dimension, you get 2 dimensions. Well, now, if we integrate the area, the cross-sectional area, and multiply that times dx, this is actually 3 dimensions, or the volume. So we want to integrate the cross-sectional area. If we integrate the cross-sectional area, integration is like taking all of those and adding them up with depth, with a 3rd dimension, but we want that depth to go to 0 for each of them, and an infinite amount of those. Just like we had our width for our rectangles, we wanted to go to 0, but then an infinite amount of rectangles, so that we got the area perfectly. Well, here we're going to get the volume perfectly with integration. There are 3 shapes that we really look at. Squares, which is side squared. We'll look at triangles, which is 1/2 base times height. And circles, which is pi r squared. So those are the 3 things you have to know. And I know you know those. You probably didn't have to write that down. I mean, I'm sure you know that. But that's where you start. That's where you start every time. You start with those 3 right there, one of those. So we want to integrate side squared from -2 to 2, from -2 to 2. But we want to do that with the variable x. So we have s squared, we don't have x squared. We need to get this in x. All right, so now let's talk about how we're going to get this in x. The sides go from the bottom of the circle to the top of the circle. See, that's one side of this square. Another one's right here, going from the bottom of the circle to the top of the circle. But the lengths of the sides are changing as you go across the circle. From here to here is, let's see, the circle is, if I minus over x squared and square root, the length of that is the square root of 4 minus x squared. Down here, this is the negative square root of 4 minus x squared. So the overall length, if I kept this as a negative, would be 0. We don't want that. Matter of fact, with length, we just count everything as positive. So the length of this right here is 2 times that. That's actually sitting right here. That's right there. So the side is 2 times the square root of 4 minus x squared squared. There we go. Now we got it in x. That's what we need to integrate to find the volume of the shape. Find the volume of the object, I should say. Is there anything about that that you just like, no, I don't get it. You lost me. Is there anything up there that you just like, no, I don't understand? So everybody's good with kind of the progression I made there? Okay. So now we just got to finish it up, right? Well, this is symmetric over the y-axis. So here's what I'm going to do. I'm going to double this. I'd rather plug in 0 than -2. Wouldn't you rather plug in zeros rather than keeping track of -2? Yeah, so anytime you have symmetry, this is what I recommend you do. Symmetry over the y-axis. 2 squared is 4, so I'll bring the 4 out here, and then that thing squared is just 4 minus x squared dx. So 8 times 4x minus 1/3 x to the third from 0 to 2. We'll kind of quickly finish this up. Let me know if I make a mistake. 8/3. If I put in 0, you get 0. Oh, let's see. 24/3 minus, oh, is that going to be an 8? Do I want that? Yeah, I think I do. All right. 24/3 minus is what, 16/3? 48, 4, 128. I think I did that right, I hope. I know I set it up right. Hopefully the math is right as well. All right, well, that's it. I mean, but now we just have to kind of practice it and show if there's any kind of slight variations on this. Let's see. This is the same concept, except now instead of squares, we just have to deal with triangles. But it really is the exact same process. Now, I don't have every possibility that I'm going to show you today, but I also have the triangle one, where, and I kind of started that one by accident. If we drop the xy, there's 4 of the equilateral triangles. So the cross sections now are equilateral triangles. Let's jump to this, showing this. Oh, let's sweep through. Here's how it's created. So we're sweeping these triangles through, and as we get across the circle, the bases are getting longer and longer and longer, and now the bases are getting shorter and shorter and shorter. And you can see that wherever there is a vertex, it kind of creates this edge to it. Here's the actual shape that we want, and here's the triangle sweeping through the object right here. I don't know, whoever made this, pretty clever. That's pretty cool. I couldn't do this 100 years. Anyway, let's reset that, go back to notes. Now let's find the volume of this. Let's look at the same region, but for this solid, each cross section perpendicular to the x-axis is an equilateral triangle. Find the volume of this solid. If it's an equilateral, this is the same length as the base, this is the base, and this would be 1/2 of the base. Where do you start? Well, what we're going to do is we're going to integrate. How about we do this, 0 to 2 again, and we'll double it. But it's 1/2 base times height. There's where you start. That's where you start. You start with the area of the shape. Just our normal area, base times height, 1/2. Got it. But we got to get this in x. That's the problem. Now, I don't want to deal with 2 different variables. I'd rather get this to be 1 variable, and we can do that. We can say that we kind of design our triangle this way. I want to h. So just by right triangle Pythagorean theorem, h squared plus this squared, which is 1/4 b squared, is equal to this squared. There's Pythagorean theorem. Subtract that over. 4/4 minus 1/4 is 3/4. And then when we square root, do you recognize that number, square root of 3 over 2? Of course you do. It's right off of the unit circle. So a equilateral triangle becomes a 30, 60, 90 right triangle. So now I can go 0 to 2. I can pull that out because I cut it in half. So half of 2 is 1. But then we have base times square root of 3 over 2 times the base. dx. But that's 0 to 2 of square root of 3 over 2 times the base squared dx. That's integral from 0 to 2 of square root of 3 over 2 times something squared. Well, it's all the way across again. Just like the square, the base of the triangle goes from the bottom of the circle all the way to the top of the circle. So that's 2 times the square root of 4 minus x squared dx. There we go. We got it set up. That's most of the battle right there. Two squared is 4. 4 divided by 2 is 2. So how about we go 2 squared of 3, 0 to 2 of 4 minus x squared dx. I feel the more constants I can get out of there, the easier the integration is. And then we just remember to multiply later. All right, 2 squared of 3, 4x minus 1/3 x to the third. I think this is going to be the same thing as before. 8 minus 8/3. So 24/3 minus 8/3. 16/3? So 32 square root of 3 over 3. I love this section. It's so cool. I love it. Tomorrow we're going to revolve stuff around the x-axis. That gets even cooler. What do we got? All right. This is right out of the book. This is number 2. And it says, find a formula for the area of the cross-section of the solid that are perpendicular to the x-axis. So we're not, they're saying don't do the integral. Just what would you integrate? What's the area you would integrate in x? Now, the planes, instead of being a circle, we're going from negative square root of x to square root of x. And that's sitting right here. So there's square root of x. Here's negative square root of x. So we don't have that symmetry on both sides. But that's all right because we're going to integrate from 0 to 4 anyway. We're already plugging in 0 if we were to integrate this. Now, this cross-section are circles. So a of x, we'll start it out as pi r squared. And notice there's no x's in pi r squared. We have to get the x's in there. But the radius of this circle, it doesn't go all the way across like the base did of the square and the triangle. It just goes from the x-axis to the curve. So the length of that radius is the square root of x. Whoops, not that one, but this one rather. So that's the length of the radius. So this is equal to pi square root of x squared. So the answer that the book is looking for is simply pi x. Now, if we were to continue on, I would integrate this from 0 to 4 of pi x dx. That would be the volume. It doesn't ask for this. But this is how we'd finish the problem. So, I don't know, that's pretty easy. 1/2 x squared from 0 to 4. 16 divided by 2 is 8. So the volume is actually 8 pi, but this is all you're responsible for if you were to do number 2 in the book. But it wouldn't take much more to find the volume, quite frankly. What would the cross-sectional area be for B? Trying that. Here, I'll start you out. A of x equals side squared. What would I write next? Go. What do you think? So unlike the radius, we need all the way across. We need all of this. Now, half of it is square root of x. The other half is negative square root of x, but the distance is also square root of x. We don't use the negative when we're talking about length. So this is 2 times the square root of x squared, so 4x. And of course, it wouldn't take much to finish it out and get the volume, but this is all they ask for. All right, you want a challenge? That's not the challenge. No, that one was pretty easy. Try letter C. I don't know how many of you'd get this one. No sarcasm either. This one's a rough one if you don't know what to do. I mean, if I don't show you what to do. It's a little rough. Here, I'll even help you with the picture. I'll let you picture it. Cross sections are squares with diagonals in the XY plane, not the sides. So very rough. I am a trained artist. Sarcasm. I don't think I'm doing too bad so far. This now is the diagonal of the square. So now I got to make it look like a square. How about like this and this and this and I don't know. I've done better, but there it is. So that's the square. The diagonals are sitting on the XY plane. Now that doesn't change what the area is. I'll even give you this. The area is still side squared, but now the answer is not going to be 4x, but what is it going to be? That's your challenge. Ooh, I see some good numbers. I see some good numbers. And if you get it wrong, you can just rewrite it. I'll tell you eventually. So here's a side, here's a side, here's a side, here's a side. This is the diagonal, right? All the way across, there's the diagonal. So here's what I would say. I would say side squared plus side squared is equal to the diagonal squared, because you have this right triangle. It doesn't look like a right triangle, but it is. So 2 sides squared is equal to the diagonal squared. So side squared is equal to diagonal squared over 2. Well, that's what we want. We want to replace side squared with the diagonal squared because that's the thing that is sitting on the XY plane. So the area, instead of side squared, I can write diagonal squared over 2. Everybody cool with that? Just Pythagorean theorem, really. Well, the diagonal is the one that is 2 square root of x. So we have 2 square root of x squared over 2. That's the thing that's sitting on the xy plane. So 4x over 2, it ends up being 2x instead of 4x. It's 2x. That is the cross-sectional area. Then we'd go on, we'd integrate that from 0 to 4. How about D? We've already kind of done it. There's a hint. The cross sections are equilateral triangles with bases in the XY plane. Can you set that one up? Well, not exactly. It's a different function though, right? Yeah. Make you think about it a little bit. So it's like, where do we even start? Well, you start with the area of a triangle, 1/2 base times height. Now, if you were asked to find the volume, you'd just start with this. You'd start with 1/2 base times height dx. But they only ask you for the area on this problem. But we said that the height is square root of 3 over 2 times the base. That's what we said before. So the overall area is square root of 3 over 4 base squared. So that's how we can get height out of there. We can base it on the base. But now the base, if we draw this, boom, boom, square root of x, negative square root of x. Here's the triangles. So that base is sitting on the xy plane right there. And that is the 2 times square root of x over 4. What did we say? 2 times square root of x squared. So this 4, when we square it, cancels out that 4. So square root of 3 times x. That's the cross-sectional area there. That's what we would integrate. These are volumes of known cross-sections. Tomorrow we'll do volumes of rotation, and then the next day, Monday, we'll do what's called the shell method. Any questions? Let's keep rolling. What else we have? Oh, I like this one because we can use a formula to check our answer. The solid lies between, so find the volume of the solid analytically. The solid lies between planes perpendicular to the x-axis at x equals -1 and x equals 1. The cross sections perpendicular to the x-axis are circular discs. Oh, it's not this one. We don't have a formula for this. It's the next one, I think. To the x-axis are circular discs whose diameters run from the parabola y equals x squared to that other parabola. We're going to find the volume. So we're going to integrate. And we can integrate from either -1 to 1, or we can double that and go from 0 to 1. Because there's symmetry. These are both parabolas that are centered across the y-axis. But we have a little bit of a problem. Well, first of all, the cross sections are circles. Pi r squared dx. Always start with the area. A formula for the area. Whether it's a rectangle, a triangle, a circle. You all right? Isn't this exciting? You look thrilled. Yes. I love this stuff. I'm sorry. I'm sorry this is not that exciting. I love it. I'm having a blast. Is there anything can I get you something? You have a drink. Yeah, you're good. Okay, never mind. That's the diameter. So we're halfway there. We're actually there, but we're too much, right? We're twice the radius. Now, in order to get this distance between the two curves, see, function values go from the x-axis. So if we get the function value for 2 minus x squared, and we subtract out the function value for x squared, that's where we're going to get this distance in between. That just happens to be the diameter of the circle. So let's go with this. Let's go 2 pi, integral from 0 to 1, of top function minus bottom function gives me that length in between. So 2 minus x squared minus x squared. So the top function minus the bottom function. But like I said, that gives us the diameter. So we want to divide all that by 2. There's the radius. And it's the radius squared. Which looks like kind of a mess. I think it's a fairly simple concept. Two things going on there. Top minus bottom gives me that little segment, but that's the diameter, so we just have to cut it in 2. Everybody okay with that? Well, I mean, that's it. Now the rest is just a little bit of algebra and a little bit of integration. So 2 minus 2x squared over 2. Factor 2 out, divide by 2. 1 minus x squared squared. 2 pi 0 to 1 of 1 minus 2x squared plus x to the 4th. So other than, here's setting it up right there. So there's setting it up. Anything after that is a little bit of algebra gymnastics, if you will. How about a little integration? X minus 2/3 x to the third plus 1/5 x to the fifth. We got to deal a little bit with fractions, but by splitting it up, it makes it a little easier because the fractions will only come from 1. If we had -1 to 1, then we'd have a whole bunch of fractions. So I really like splitting it up when you can. 1 minus 2/3 plus 1/5. Let's see, 15/15 minus 10/15 plus 3/15, 8. So 2 pi times 8/15. So 16 pi over 15. Any questions? Is this the sphere? This is the sphere. The solid lies between planes perpendicular to the x-axis at x equals -1 and 1. The cross section is perpendicular to the x-axis. Between these planes run from the semicircle this to this. The cross sections are circular discs with diameters in the xy plane. So this is our sphere. So let's find the volume using calculus, and then we'll use the formula because it's a sphere. This only asks for the area, by the way. So we're kind of going a little bit beyond the instructions on this one. So we want to integrate from, how about 0 to 1 and double it, because we have symmetry. From -1 to 0, 0 to 1, there's symmetry there. Pi r squared, because the cross sections are circles. So the base is a circle and the cross sections are circles. That's what a sphere is. We got to get the radius though, and the radius only goes halfway. For like triangles and rectangles, we got to go all the way with this. But we only need this for the radius. 2, 0 to 1, pi, 1 minus x squared squared dx. So there it is set up. Everything else is now just our old, a little bit of algebra, a little bit of integration. 1 minus 2x squared plus x to the fourth. Oh, wait. Nope, I made a mistake. The square should be gone, right? It's my square, the square root. Square root of 1 minus x squared. My apologies. There, that's what it should be. 2 pi, 0 to 1 of 1 minus x squared dx. There we go. I knew that wasn't going to end up right. 2 pi x minus 1/3 x to the third from 0 to 1. And 2 pi times 1 minus 1/3. So it'll be 1 minus 1/3 when we plug 1 in. When we plug 0 in, we get zeros. So that's 2/3. So 4 pi over 3 is the volume of that sphere. Anybody know what the volume of a sphere is? The equation, the formula? 4/3 pi r cubed. And our radius is 1. So 4/3 pi times 1 to the third is 4 pi over 3. There we go. But we got it using calculus. I don't think on a test you're going to find the volume of a sphere. You just use the formula. But it works. How about the cross sections are squares with bases in the xy plane? Just find the area. Can you do that? Don't integrate it. What would the area be? What would the cross-sectional area be? Side squared to begin with, right? Side squared. Now we just need the side, which is 2 times circle what? Radius 1, if I remember right? Yeah, 1. 2 squared of 1 minus x squared squared. So 4 times 1 minus x squared. And we could distribute the 4 through, but it doesn't matter. Questions on that? No, go ahead.
Where's the 2 come from?
Where's the 2 come? Oh, from here to the edge of the circle, the length is the square root of 1 minus x squared, but we got this other one over here. There's 2 of them, 2 lengths of those. You're welcome. What about, let's practice, what if the diagonal is on the xy axis? What about that one? They give you a hint, but forget the hint. We don't use the hint. We don't need no stinking hint. So the area is still side squared, right? Thank you. I think you won the cake raffle. Good job. Didn't we say that side squared is equal to the diagonal squared over 2? So that's what we can replace this with. So diagonal squared over 2. But the diagonal, this is the 2 times the square root of 1 minus x squared. So this is 2 times the square root of 1 minus x squared squared over 2. That's 4 over 2, that's 2. Oops, we don't have the square root anymore. So 4 over 2 is 2, 1 minus x squared. There's the cross-sectional area of that. How about the equilateral triangle? Fine, give the area of that. So in other words, we're not doing the integration part. So 1/2 base times height, right? That's where you start. You start with the formula for the cross-sectional area of the shape that we have. There's a triangle. And we said that h is square root of 3 over 2 times the base. So the area is 1/2. Let's do this. Well, I won't skip steps. b square root of 3 over 2 times b. That's h, right? So we have square root of 3 over 4b squared. But I need that in x. So square root of 3 over 4, this is the 2 times square root of 1 minus x squared squared. That's the base. That's what's sitting on the xy plane. So 2 squared is 4. So we have square root of 3 times 1 minus x squared. Questions? Hopefully we've practiced that enough that you kind of, hopefully it's getting a little easier. The couple, what time we get out of here? 26? All right, we might be able to do this one right here. Let's try to get this one done and then we'll be good. This is an example of a free response question. I thought A is just finding the area. We're going to skip that. That's old stuff. Region S is the base of a solid whose cross sections perpendicular to the x-axis are squares. Find the volume of the solid. So here's area S. So there's the base of a square. Now if we laid this down, these squares are coming up off of the base like this. So there's one square. Now we're supposed to integrate this. We're finding the volume. So we're going to integrate from this intersection I, whatever x would be, to 2. We'd have to calculate that intersection. We are going to do that. But now the length of the base is the top function minus the bottom function, because really all these function values start at the x-axis. So we have the distance to the top function, subtract out this distance right here, and you're left with what's in between. Now that curvy one, that is the x to the 4th. The one that just kind of this U shape, that's the e to the x. So f of x, oh wait. We're integrating side squared. That's the area of the square. Now to get that side, that's where we subtract. So it's f of x minus g of x squared dx. So let's grab our calculators and let's actually get this answer. So we have a little more practice of using the calculators. Clear. I'll pretend I haven't done this yet. Our first step on this one, I think, is to get that intersection point so that we know what to integrate from. So let's go y equals, let's put f in y1. 1 plus x plus e to the x squared minus 2x. Enter. And now I can't see that other function. Let's grab over here. X to the 4th minus 6.5 x squared plus 6x plus 2. If we look at, oh, that's too small. There we go. The window, probably what, 0 to 2, let's go 0 to 3, 0 to 5. So 0 to 3 by 1s, 0 to 5 by 1s. Seems to be kind of what their window is. Maybe a little smaller than that. Graph. There's the e to the x1, there's the x to the 4th. Now we know that this x value is 2, we just don't know that x value. So we're going to calculate intersection. Enter. 1.032. 1.0328. 1.0328. It's important to write out on your, like for your response questions, it's important to write out what you're doing on the calculator. You can't have what they call bald answers. In other words, you just type in your calculator, you write a number down. That's usually going to get you 1 out of 2. But now the good part is that x holds that value. So if we go to the home screen, if you're to just enter x, it's holding that value. So now we're going to go math number 9. We're going from x to 2. Parentheses, variables, VARS, y1 minus VARS again. If you arrow over, function y2. And then we're going to square that, because that's the side. There's side squared. That's the area of the square. And you're just going to have to take my word for it that that's the right answer. That's what I've been getting all day, too. So 1.283. There we go.